All right, this is chapter 19, problem 40. And here what we're told is that there's a 21.0 voltage source applied across a whole network as drawn in this picture with three different capacitors, right? These two capacitors are in series with each other. They in turn are in parallel with this capacitor C3. And we are tasked with figuring out the voltage across each capacitor and the charge on each capacitor as well. It may be helpful right away to draw a picture, to think about what's going on here. Remember, on each capacitor, and just for sake of argument, let's assume that this voltage source is supplied so that the positive voltage here, negative voltage here, or at least what we're saying is this point over here is at a voltage of 21 volts higher than this point over here. What that means is there's a buildup of positive charge, if you like, connected to the positive side, negative charge to the negative side. What I can do is I can go ahead and call this, I'm going to call this plus Q3 over here and minus Q3 over here. These should have the same magnitude as opposite. Likewise, I'll call this Q1 and a minus Q1 on capacitor number 1, and a Q2 and a minus Q2 on capacitor 2. So that's the most general thing that you can write down. We're supposed to figure out the voltage across each capacitor. So first, let's just the voltage across each capacitor and the charge on each one. The first thing we should do is analyze this first capacitor here. This is the easiest one to think about because, well, the voltage across this capacitor is the full 21 volts. If you take your finger, this is a 21 volt difference. I'm going across a perfectly conducting wire. I get to the capacitor, and that is the voltage difference from one side to the other. So let's think about this. The equation that we'll need to relate capacitance and charge and voltage is this generic equation. CQ divided by delta V, and I may switch the notation occasionally on accident and just do Q over V, but that's the basic, if you like, definition of capacitance, and it relates charge and voltage. So for Q3, or the Q3 slash capacitor number 3, what we have, the voltage difference is the full 21 volts. So that's simply the answer for that. To find the charge, all we would need to do is use this equation. We know the capacitance, we know the voltage, and so if you like, we can write that the charge, Q3, is apparently C times delta V. The C is the capacitance of that capacitor. The delta V, it's that, I'll put delta V3. It's that number, and so what we have here, C3 is 2.0 times 10 to the minus 6 farads times a voltage of 21.0 volts. It should be, these are the SI units for capacitance and voltage. A farad times a volt had better have the units equivalent to coulombs, and so when you work this out, you'll find that, well, this will give you 42 times 10 to the minus 6 farads. So if you want, you can write this as 42.0 times 10 to the minus 6 farads, or 42.0 microfarads. Sorry, that's not a farad, that's of course a coulomb, that's what I just said. So if you like, that's answer A and B for capacitor 3. The next thing I'm going to do is actually point out that although in general you can, if you didn't know anything, you could write down that capacitor 1 and 2 have their own charges, Q1 and Q2, you got to realize, if you just focus especially on this inner part, that there's no way that these magnitudes of charge can be any different, because this whole piece, if you like, the plate of this capacitor, the plate of this capacitor, and the wire in between should have a net charge of 0, which means that these charges really must be equal in magnitude. So I'm going to go ahead and actually now erase the subscript 1 and 2. These charges must be the same, and recall that the total charge or net charge in a capacitor should be 0. So if that's Q, this should also be Q. If you like, Q and minus Q, Q and minus Q. So what we're really asking about now is what's the charge on any one of these capacitors, and then separately, what is the voltage? Okay, so in order to do that, what we probably want to do is think about this object as an effective capacitor or equivalent capacitor. So to do that, you have to remember that getting equivalent or effective capacitance, I'll write it as equivalent capacitance. There's this funny rule that when we add in parallel, the capacitance just adds. But in series, the inverses add. Okay? This is, by the way, opposite to the way that resistors add in parallel and series. So with that in mind, we can imagine this piece here as looking like some equivalent capacitor with some charge on the left and right. That charge, by the way, though, that's going to be this same charge Q. If you like, it's the Q from this plate, and on the other side, it's the minus Q from that plate. So it's, in other words, the same charge that you're still dealing with. And now we can ask, well, that's the equivalent capacitance. It's related to the charge, and apparently it's related to the voltage. What voltage? Well, that voltage is the full 21 volts that you get from the voltage source. In other words, the total voltage across this thing is, well, it's 21 volts. If we want to now find what the charge is, we can simply use this equation. We can write C equivalent times delta V. That should give us the charge. And we're almost ready to do that. Why don't we solve for what the equivalent capacitance of this circuit is? Apparently, this is equal to 1 over C1, right? That's 1 over 3.00 microfarads plus 1 over 4.00 microfarads. 1/3 plus 1/4, I suppose we can multiply this. This is the same as 4 over 12. I multiply top and bottom by 4. That's 4 over 12 over microfarads. Multiply top and bottom by 3. That's 3 over 12 microfarads. So this is 7 over 12 over microfarads for the inverse of the equivalent capacitance. That means that the equivalent capacitance is equal to 12 over 7 microfarads, and that's what we can plug into this. Apparently 12 over 7 microfarads times the voltage of 21.0 volts, that should give us Q, and that number turns out to be 36 microcoulombs when you plug in the numbers there. 21 over 7, that's 3. 3 times 12 is 36. I guess that's where that comes from. 36 microcoulombs for the charge. And the last thing now to do is to figure out what the voltage is on each of these. Well, now we can actually do that. If you want to go back and analyze any one of these capacitors, we know the charge on each capacitor is 36 microcoulombs. We know the capacitance of each capacitor, those numbers that were given, and we can again use our equation that relates capacitance, charge, and voltage. So let's do that last piece over here. In fact, we'll summarize the results at the end. So for capacitor number 1, we're trying to find the voltage. Apparently the voltage is equal to the charge. The voltage for capacitor 1 is the charge there, that's just Q, this number, divided by the capacitance. Okay, that is, if you like, I'll write that as 36 times 10 to the minus 6 coulombs divided by the capacitance of the first one, which is 3.00 times 10 to the minus 6 farads. The 10 to the minus 6's cancel. 36 over 3 is 12, and so apparently the voltage on the first capacitor, that's simply 12.0 volts. And the same thing can be said, of the same process for the second capacitor. Delta V on the second one is equal to its charge, well that's just Q, divided by the second capacitance, that's the 36 times 10 to the minus 6 coulombs divided by the capacitance, which is 4.00 times 10 to the minus 6 farads. The 10 to the minus 6 is cancel. 36 over 4, that's 9. This is apparently 9.0 volts. Does this make sense? Well, it should be. Remember, you can think about the Kirchhoff's loop rule. If you started here and you went, you started at some voltage, you went around, and the voltage should go up by some amount here, up by some amount here, and when I get to this point, I should be 21 volts higher. In other words, does the voltage from here to here and here to here, do they add up to 21 volts? Yes, the 12 volts plus 9 volts do add up to 21 volts. So, in summary, what do we have? C1, we have Q is equal to 36 microcoulombs, and the voltage we found to be 12 volts. For C2, we found the charge to be the same, 36 microcoulombs, and the voltage to be 9 volts. And for capacitor number 3, we have the charge, which was the 42 microcoulombs, and the voltage for that one was the full voltage of 21.0 volts. And that would be your final answer.